there are reactions like this reaction. It's not really a reaction, it's a process. This is endothermic. There's no way around it. If you want ice to melt, you need to put heat into it. So it's an endothermic process, but if I put an ice cube here and I step away from it, it will melt spontaneously. Although it's endothermic. Will a piece of ice always melt if you set it down on a table? Give me an example.
Cold condition.
Yeah, if it's cold. If we walked outside right now and it was 31 degrees, I could put the ice on the table and we'd just all sit and watch, okay, what are you going to do? Nothing. It's not spontaneous under some conditions, but it is spontaneous under some conditions too. So, they're trying to melt ice down there. So anyway, just know that some endothermic processes are spontaneous though. And that there are two factors that go into, well, really three factors that go into whether reactions are spontaneous. One is the enthalpy change. Two is the entropy change, which we talk lots about. And the last one is the temperature. So the only difference between me setting an ice cube down in here versus me going outside and setting an ice cube down is what the temperature is. The enthalpy change, and the entropy change are both the same. Yeah?
Are all exothermic processes one?
No, not all of them. No. If it has an unfavorable entropy change, it might not be. All right, so here it is. Some of you, even in other classes, I think, are telling me, oh yeah, I've saw that before. This is an example of a natural state for a dorm room.
I like the computer.
This is kind of an old computer. It's good. A dorm room will spontaneously take on this condition. This is very natural. Nature tends to become more messy. When it's fall and leaves fall off the trees, they don't pile themselves up very neatly for us to just put into bags. They fall all over the yard, and so we have to put them all into a more ordered arrangement in order to bag them up. So this is very natural. Okay. So entropy, we'll talk for the rest of the hour about entropy. Entropy is a measure of how random or disordered matter is. If I were a chemistry purist, pure chemistry people don't like that whole idea of disorder. That really isn't the complete theoretical definition of what entropy is. Entropy is a pretty abstract concept. It doesn't have a nice definition. So we use the word disorder because everybody, even if you're not very advanced in chemistry, you can understand what disorder is. And it's something that we all understand. And it's close enough to the definition of what entropy is. Entropy's official definition involves particle motion and probability, and it's a very, very mathematical, abstract definition. We'll just call it disorder. The Zumwalts even just call it disorder. So if you've ever learned about entropy before, I'm thinking you've learned these things. What increases entropy in a reaction? To produce gases makes more entropy. To go from fewer particles into more particles, that's breaking things up, that increases entropy. And even dissolving a solid is kind of like number one there, where the solid particles, when they dissolve, are broken apart, like when a solid becomes a gas. Yes?
So, like, taking a huge chunk of salt and breaking it increases entropy?
Yes, it's more disordered when it's gone into several pieces.
But aren't they still, like, NaCl ions, and they're still, like, tightly packed?
Yes, that's right. Yep.
It's not really a random, more random.
Yeah, it is.
They're the same.
They are.
Yeah. They were ions, they still are ions. They haven't, like, you know, like, increased. Like, for example, when the gas starts moving faster, it's not, like, connected to anything.
If if crushed up salt is the same as one big chunk of salt, how do you get from one big chunk of salt into crushed up salt? Just watch it and poof, it happens? What do you have to do? You have to exert a force and energy into it. You have to put energy into it. So they're not the same then, are they?
No, but so it means it's not
I
stuck,
know.
right?
I know what you mean. Chemically, they're the same thing, and I'm not saying they're not. They are. Physically, they're not the same thing. And so, yeah, it does. Yeah, and usually with entropy changes, we're talking about a chemical change, a chemical reaction, which is different from the example that you gave. Okay. Here's a couple other things about entropy that we need to know. If you heat up a substance, that should cause its entropy to go up because the particles are moving faster, and the faster things move, the more random their motion or their behavior is. Since entropy is affected by the flow of heat, then, we're not only going to worry about the entropy change of the systems, the entropy change of the surroundings is also going to be very important to us. Sometimes it's the entropy change of the surroundings that's going to drive a reaction to occur, which is strange. Why would the surroundings affect whether the reaction? Well, it does. There's the law of thermodynamics, the second law, that's going to say that, the entropy, no matter what it is, whether it's the system or the surroundings, if it goes up, it's probably going to cause the reaction to occur. Now, we also have this third delta S, the delta S of the universe. This is equal to those two added together. System plus surroundings makes up the universe. Yes. Yep. I have just a picture. This is a picture of something that's exothermic. It's giving off heat. What would you say about the entropy of the surroundings as this process happens in the system? What would you say about the entropy of the surroundings? Would you agree that the surroundings are getting heat? The surroundings are gaining heat. So if the surroundings is gaining, what is it? The surroundings are gaining heat. I guess it's plural. The surroundings gain heat. What's happening to the surroundings entropy? It's going up. That's right. And so sometimes a reaction is going to occur just because the surroundings are going to increase in entropy. Yeah. So entropy is affected by heat flow. Okay. Now we have to define entropy. I only have about 15 minutes to do this. We've got to hustle along. German guy, Ludwig Boltzmann. What do you think? Huh? Shout out to the Germans. You ever hear of Boltzmann? No? Okay. Okay. Very smart guy, like Philip. Boltzmann was the first person, or not, he was not. There was a guy before him named Clausius. His first name was Santa. Anyway. That really is not funny, but I just laugh at it anyway. I don't know. Clausius came up with the first model for what entropy was, but Boltzmann came along and gave a physics/mathematical model, and it's good. It's geeky. You're gonna feel like a geek when I talk to you about it because it's like, oh my gosh, you have to go through all this. But yes, we do. Boltzmann thinks that entropy is a function of what? Probability, from statistics. Imagine that we have a system set up like this. I'm stealing this from the Zoom dolls. This is not my own creation. I like it, so I'm taking it from them. You'll see this in the book. I don't know. They draw better than me. Imagine that you have a two bulb system. This is a container that looks like this, where there's gas particles in it. Imagine that there's 4 gas particles. And I'm going to, they could be the same substance, they might be different. I'm going to make them all look different. One of them is a triangle, one is a star, a circle, and a square. Gas particles are free to move anywhere, aren't they? They're just always in constant motion. We learned that in the gas law chapter. Is it possible that all 4 particles would wind up being in the same bulb? Is it possible?
No.
Yeah, we'd say that it's possible. If the particles are in free random motion, you might have an instance where they're all together in the same bulb, and then there's nothing over there. That's possible. Is it also possible that one of the particles could be over there? We'd have 3 on one side and 1 on the other. That's okay too, right? What's more likely?
The 2 and 1.
You think this is more likely than the one where 4 are on one side and 0?
Yeah.
Because when you had all 4 over here, that's the only possibility for 4 being over there. But when you have 3 on one side and 1 on the other, how many possibilities really exist to have 3 here and 1 there? 4. There's 4 possibilities. One possibility is the way that we see it, where the other 3 out here and the star is the one that's over on the right side representing the single. Then you can also have the star still over there with the others and the square. There. That's not the triangle. That's also possible. We still have 3 and 1, but it's not the same particle. So this is going to allow us now. You're not going to be tested on any of this model. Don't write anything now until I tell you to. You might not have to write anything the rest of the hour. I want to go ahead and redraw my 2 bulb system. Not very good.
Were they supposed to be empty?
Yes.
They were
Was it my drawing or was it? Oh, they were all filled in? Yeah, well, you know what's going to happen now. Okay, so I'm going to consider the different conditions to be called macro states. You know the difference between macro and micro? Macro is big and micro is small. Micro refers to very, very fine details, where macro is like the big picture. So the macro state number 1 is the condition where remember, we've got 4 particles. 4 on one side and 0 on the other would be macro state number 1. Doesn't matter which is where, it's just a macro state. Macro state number 2 is where you have 3 on one side and 1 on the other. That's where I quit on the last slide. Macro state number 3 is where you have 2 and 2. Number 4 is where you have 1 on the left and 3 on the right. And 5 is where you have 0 on the left and 4 on the right. Are there any other possibilities for the arrangement, assuming that the particles cannot be in there at any given time? No. Okay. So if I had all 4 of the particles there's only one possible arrangement, and that's it, right? So for the macro state number 1, there's only one possible micro state, or as I said up there, configuration, just to have all 4 on that side. If I have 3 and 1, I was afraid of that. There's 3 and 1. How many possible microstates are there? We decided there were 4. What if I have 2 on one side, and 2 on the other side? There are there 6? Do we agree that there's 6, or should we count them up? To have 2 on one side and 2 on the other side, here are the possible combinations. You can have the triangle with the circle. There's one. The triangle with the star, and then the circle and star would be switched. So that would be the second one. The triangle with the square, that's a third one. Or you can have the circle with the star, that's a 4th. The circle with the square, that's the 5th. Or you can have the star with the square over here on the left, that's the 6th. I don't think there's any other possible combination. You have 2 and 2. What's your
What if they flip sides? Wouldn't gonna be 12 then? Because that's what we said for.
They switch sides. Like, if they switch sides, then that's the same thing as having the star and the square on the left.